Bitcoin secures over $700 billion in value through 256-bit cryptography. At this scale, the number of possible private combinations is so vast that the network has remained secure against every traditional computational attack in its history. To guess a single private string through brute force, a classical supercomputer would need to run for trillions of years, well beyond the current age of the universe. That assumption of safety was recently challenged. Giancarlo Lelli, an Italian researcher, successfully derived a private string from a public key using a quantum computer accessible to the general public. Lelli was awarded 1 Bitcoin from the Project 11 bounty program after his software resolved a 15-bit elliptic curve problem in under 10 minutes. This chart highlights the acceleration. While a 15-bit string is far smaller than the 256 bits protecting a standard wallet, this successful derivation is 512 times larger than previous public demonstrations, which were limited to simple arithmetic, like factoring the number 21. If quantum hardware continues this trajectory toward the 256-bit standard, 6.9 million Bitcoin currently held in addresses with visible public keys will be exposed to immediate unauthorized transfers. This makes Q-Day, the hypothetical moment quantum systems can bypass modern encryption, a live active countdown for the entire crypto economy. Most blockchains rely on elliptic curve cryptography. This system uses mathematical functions that are easy to perform in one direction but become computationally expensive to reverse, creating a secure one-way link between your public identity and your private access. The primary threat to this structure is Shor's algorithm. This is a specific set of instructions designed to run on quantum hardware that identifies the period of a function to find the underlying factors of a large number. Unlike a classical computer that tests one solution at a time, a quantum system using Shor's algorithm evaluates the entire mathematical space simultaneously. It calculates the private values by observing how the algorithm interacts with all possible states at once. This process requires qubits, units of data that can represent 0 and 1 at the same time. The machine used for the 15-bit demonstration operated with 70 qubits, providing a glimpse of the hardware scaling currently underway. Since elliptic curve math secures most digital assets, Lelli's success is the first measurable sign of stress on the network's structural integrity. Estimates for when this technology will reach maturity are shifting. Google recently moved its internal target for transitioning to quantum-resistant encryption up to the year 2029. This revised timeline isn't just larger computers, it's a shift to hyper-efficient architectures that require fewer resources. Researchers at Caltech have been documenting a neutral atom architecture. While previous models suggested 500,000 physical qubits were needed to compromise Bitcoin, this new design could potentially reach that threshold with only 10,000 to 20,000. The final barrier, stabilizing these systems, is now being addressed through AI-driven error correction. These models identify and correct computational noise in real time, allowing quantum machines to stay stable for longer periods without human intervention. The combination of neutral atom designs and autonomous error correction means the computational power needed to resolve 256-bit keys is arriving much faster than earlier models predicted. Developing a defense for Q-Day has become a high-stakes engineering deadline for blockchain protocols. Developers have a limited window to implement these critical upgrades before the quantum hardware reaches a critical mass. Several network upgrades are currently under review. Proposal BIP 360 introduces a new transaction format designed to resist quantum derivation. Proposal BIP 361 suggests phasing out older signature schemes, eventually freezing coins that haven't migrated to new addresses to prevent them from being stolen. Researchers at Starkware have proposed a quantum-safe Bitcoin method. This would allow users to secure their transactions using the existing protocol rules, potentially avoiding the need for a contested or disruptive network fork. The 15-bit demonstration serves as a definitive warning. Bitcoin has the technical capacity to survive the quantum age, but the network must update its underlying signatures before the quantum hardware catches up to its current defenses.